Hello there, welcome to Deep Science Sleep. Take a moment right now to settle into your bed, your pillow, your blankets. Feel the weight of your body sinking down into the mattress beneath you. Let your muscles release their tension one by one. Your shoulders can drop. Your jaw can unclench. Your breathing can slow to a gentle, natural rhythm. Tonight, we're going on a journey together, but not the kind that requires any effort from you. No, this is a journey of relaxation, of wonder, of drifting peacefully into the realm of atoms, those impossibly tiny building blocks that make up everything around you and everything within you. We'll discover how scientists learn to split these minute pieces of matter, but we'll do so in the gentlest possible way, letting the story wash over you like waves lapping at a quiet shore. There's no need to remember every detail. There's no test waiting for you in the morning. This is simply an opportunity to let your mind wander through one of the most fascinating chapters in the history of science while your body prepares itself for deep, restorative sleep. So close your eyes if you haven't already, or let them grow heavy as we begin, and allow yourself to drift wherever this story takes you. The poetry of atoms. Let's start with something extraordinary, something that connects you to the entire universe in the most intimate way possible. Right now, as you lie there in the darkness, your body contains approximately 7 octillion atoms. That's 7 followed by 27 zeros. It's a number so vast that it loses all meaning, becomes pure abstraction. But here's what makes it beautiful. Every single one of those atoms has a story stretching back billions of years. An atom is the smallest unit of matter that still retains the properties of an element. Think of it as a tiny letter in the alphabet of existence. Just as 26 letters can combine to create every word in every book ever written, a little over 100 different types of atoms can combine to create everything in the known universe, from the distant stars flickering in the night sky to the soft pillow cradling your head right now. Each atom is composed of even smaller components, arranged in a structure of remarkable simplicity and profound elegance. At the center lies the nucleus, a dense core containing protons and neutrons. Protons carry a positive electrical charge, while neutrons, true to their name, are neutral, carrying no charge at all. These particles are bound together by one of the fundamental forces of nature, holding tight in an embrace that defines the very identity of the atom. Surrounding this nucleus, in regions we call orbitals, are the electrons. These tiny particles carry a negative charge, perfectly balancing the positive charge of the protons when the atom is in its neutral state. But here's where it gets truly mesmerizing. Electrons don't orbit the nucleus like planets around a sun, despite what many old textbooks might show. Instead, they exist in clouds of probability, regions of space where they're most likely to be found. They're more like a blur of possibility, a quantum fog surrounding the nucleus. The nucleus itself is remarkably small. If you were to expand an atom to the size of a large sports stadium, the nucleus would be about the size of a small marble sitting at the center of the field. All that empty space between the nucleus and the electrons, all that apparent nothingness, makes up more than 99.9% of the atom's volume. You are mostly empty space. The chair you're sitting on or the bed you're lying in is mostly empty space. Everything solid that you touch, everything you see, is mostly the vast emptiness between these tiny particles. But that emptiness isn't truly empty. It's filled with electromagnetic fields, with the probability clouds of electrons, with quantum fluctuations that pop in and out of existence too quickly for us to measure. It's a space humming with potential, vibrating with forces that keep matter stable and prevent you from falling through your bed or walking through walls. Consider the hydrogen atom, the simplest atom in existence. It has just one proton in its nucleus and one electron dancing around it. Hydrogen makes up about 10% of your body by mass, but because hydrogen atoms are so light, they actually account for about 62% of all the atoms in your body. Every breath you take contains countless hydrogen atoms that have been part of other living things, other people, other moments in history stretching back through time. Then there's carbon, element number 6 on the periodic table. Carbon atoms have 6 protons in their nucleus, usually 6 neutrons, and 6 electrons surrounding them. Carbon is extraordinary because of its ability to bond with other atoms in countless ways, creating the complex molecules that make life possible. The carbon in your DNA, in your muscles, in every cell of your body, was forged in the hearts of ancient stars. We'll explore that cosmic connection more deeply in just a moment. Oxygen, with its 8 protons and typically 8 neutrons, makes up about 65% of your body by mass. Right now, as you breathe in and out, you're bringing oxygen atoms into your lungs where they'll bind to hemoglobin in your blood and travel throughout your body, participating in the chemical reactions that power every function, every thought, every heartbeat. The atoms in your body are not permanent residents. You are constantly exchanging atoms with the world around you. When you breathe, you release carbon dioxide, sending carbon and oxygen atoms out into the air. Someone across the world might breathe in those atoms tomorrow, next week, next year. When you drink water, you're incorporating hydrogen and oxygen atoms that might have been part of a cloud, a river, a dinosaur drinking from an ancient stream. The atoms you ate for breakfast become part of your cells, replacing atoms that are shed or expelled. This constant exchange is happening right now as you lie there. With each breath, you're bringing in oxygen molecules from the air around you. Those molecules contain oxygen atoms that might have been in the ocean last week, converted to gas by photosynthesis in microscopic algae. Before that, they might have been part of a fish, or dissolved in rainwater, or locked in ice at the poles for thousands of years. Each atom has its own journey, impossibly complex, winding through the biosphere. The water you drank today, maybe this evening before bed, contained hydrogen atoms that are among the oldest things in existence. Those hydrogen nuclei, simple single protons, were created in the first moments after the Big Bang. They've been recycling through the universe for nearly 14 billion years. They might have been in the early solar system's cloud of gas and dust, then in comets that bombarded the young Earth, delivering water to our planet. They might have been in ancient oceans, in the bodies of trilobites crawling on Paleozoic seafloors, in the rain that fell on the day you were born. In fact, most of the atoms that make up your body right now weren't part of you 7 years ago. You are continuously renewed, rebuilt, reconstructed from the matter around you. And yet, somehow, you remain you. Your memories persist. Your sense of self continues. You are a pattern, a process, a story told in the language of atoms that are constantly arriving and departing, but the narrative remains coherent. This is one of the most profound mysteries of identity and consciousness. The physical substance changes, but the pattern persists. It's like a whirlpool in a river. The water molecules making up the whirlpool are constantly flowing through it, constantly being replaced by new water molecules. Yet the whirlpool itself maintains its shape and identity. You are a whirlpool in the flow of matter, a stable pattern in an ocean of atoms. Your DNA, the molecular instruction manual for building and maintaining your body, is itself made of atoms. The famous double helix structure consists of two long chains of sugar and phosphate groups, connected by pairs of nucleotide bases. All of this built from carbon, hydrogen, oxygen, nitrogen, and phosphorus atoms. These atoms bond together in specific ways because of the arrangement of electrons around their nuclei, because of quantum mechanical rules governing how electrons can be shared between atoms. The information in your DNA, the sequence of nucleotides that makes you unique, has been passed down through generations. Some of the information in your DNA comes from ancestors who lived thousands of years ago, tens of thousands of years ago, ultimately tracing back to the first self-replicating molecules billions of years ago. But the actual atoms making up the DNA molecules in your cells right now, those atoms have been replaced many times throughout your life. The pattern is inherited. The material is borrowed temporarily. The mass of an atom is concentrated almost entirely in the nucleus. A proton and a neutron each have a mass of approximately 1 atomic mass unit, while an electron weighs only about 1/1800th of that. This means that despite taking up nearly all the space of an atom, electrons contribute almost nothing to its mass. The weight you feel when you step on a scale comes almost entirely from the protons and neutrons in your body's atoms. Different atoms of the same element can have varying numbers of neutrons. These variants are called isotopes. Carbon-12, the most common form of carbon, has 6 neutrons. Carbon-14, used in radiocarbon dating to determine the age of ancient artifacts, has 8 neutrons. Both are carbon because they both have 6 protons, but that difference in neutrons gives them different properties. The number of protons in an atom's nucleus defines what element it is. Change the number of protons and you change the element entirely. An atom with 1 proton is hydrogen. Add another proton and suddenly you have helium, an entirely different element with completely different properties. Add another and you have lithium. This continues all the way up through the periodic table to the heaviest natural element, uranium, with 92 protons. The forces holding atoms together are extraordinary in their strength. The electromagnetic force binding electrons to the nucleus is powerful, but the force holding protons and neutrons together in the nucleus, called the strong nuclear force, is even more remarkable. It has to be because protons, all carrying positive charges, would naturally repel each other. The strong force overcomes this electrical repulsion, but only at extremely short distances measured in femtometers, a unit so small that it takes 1 trillion femtometers to make just 1 millimeter. Understanding atoms required centuries of human curiosity, experimentation, and insight. Ancient Greek philosophers proposed that matter was made of tiny, indivisible particles they called atomos, meaning uncuttable. They were wrong about atoms being indivisible, as we'll discover, but remarkably prescient about their existence. It took until the 19th century before chemists like John Dalton began to build scientific theories about atoms based on careful measurements and observations. As you lie there, feeling your breath move in and out, you're experiencing the flow of atoms. Air molecules, mostly nitrogen and oxygen, drift into your lungs. Your body extracts what it needs and releases what it doesn't. This exchange happens automatically, effortlessly, powered by the movement and interaction of countless atoms following the laws of chemistry and physics. You don't have to think about it. Your body knows what to do. And as you relax more deeply, your breathing slows, becomes more regular, more peaceful, and the atomic dance continues, unnoticed, eternal. Ancient stardust within us. Here's a truth that sounds like poetry but is actually rigorous science. You are made of stardust. Not metaphorically, not symbolically, literally. The atoms that compose your body, with few exceptions, were created in the nuclear furnaces at the hearts of stars that lived and died long before our sun existed, long before Earth formed, long before life began its journey toward complexity and consciousness. In the beginning, approximately 13.8 billion years ago, the universe began with what we call the Big Bang. In those first moments, as the universe expanded and cooled from its initial state of unimaginable heat and density, the first atomic nuclei formed. But the early universe was simple. It contained almost exclusively hydrogen, the lightest element, with one proton in its nucleus. It also contained helium with 2 protons and trace amounts of lithium with 3 protons. That was essentially it. 3 elements to build an entire universe. For hundreds of millions of years, the universe contained only these simple elements, drifting through space as vast clouds of gas. Eventually, gravity began to pull these clouds together. Where the gas grew dense enough, the pressure and temperature at the center increased until something extraordinary happened. Nuclear fusion began. The first stars ignited, and the universe lit up. Inside these stars, hydrogen nuclei fused together to create helium, releasing tremendous amounts of energy in the process. This fusion reaction is what makes stars shine, what makes our sun warm your face on a summer afternoon. But the story doesn't end with helium. As stars age and their hydrogen fuel begins to run low, they start fusing helium into heavier elements. Helium nuclei combine to form carbon. Carbon combines with helium to make oxygen. Further fusion creates neon, magnesium, silicon, and other elements, step by step up the periodic table. This process of stellar nucleosynthesis, as scientists call it, takes place over millions or billions of years, depending on the size of the star. Larger stars burn through their fuel more quickly, while smaller stars can shine for trillions of years. Our sun, a medium-sized star, has been burning for about 4.6 billion years and has roughly another 5 billion years of hydrogen fusion ahead of it. But there's a limit to what normal stellar fusion can create. The element iron, with 26 protons, represents a sort of endpoint. Fusing elements lighter than iron releases energy, making it favorable for the star. But fusing iron into heavier elements would require energy input rather than producing energy. So stars build up iron in their cores, unable to fuse it further through normal processes. For the most massive stars, this creates a crisis. The iron core grows until it can no longer support itself against gravity. In a fraction of a second, the core collapses, creating conditions of such extreme temperature and pressure that the laws of physics bend in extraordinary ways. The collapse happens so rapidly and violently that it generates a shock wave that tears through the star's outer layers, creating what we call a supernova, one of the most energetic events in the universe. In that brief moment of catastrophic explosion, something miraculous happens. there's finally enough energy to create elements heavier than iron. Gold, silver, platinum, uranium, and all the other heavy elements are forged in seconds during the supernova explosion. The shockwave blasts these newly created elements out into space at tremendous speeds, seeding the cosmos with enriched material. This ejected matter, containing all these varied elements, drifts through space, mixing with clouds of hydrogen and helium gas. Eventually, gravity pulls these enriched clouds together, and new stars form. But these second or third generation stars are different from the first stars. They contain heavier elements from the beginning, elements that were not present when the universe was young. Our Sun is one such later generation star. It formed about 4.6 billion years ago from a cloud of gas and dust that contained not just hydrogen and helium, but carbon, oxygen, silicon, iron, and traces of every other element up to uranium. This cloud collapsed under its own gravity, forming a disk of matter. At the center, our Sun ignited. In the disk surrounding it, particles of dust began to stick together, slowly growing into pebbles, then boulders, then planetesimals, and eventually planets. The Earth condensed from this primordial material about 4.54 billion years ago. Every atom of iron in Earth's core, every atom of silicon in its rocks, every atom of oxygen in its atmosphere, came from the death of ancient stars. The calcium in limestone cliffs, the gold in buried veins, the uranium in radioactive ore, all of it was forged in stellar furnaces and scattered across space by supernovae. Imagine, if you will, the journey of a single carbon atom now part of your body. Perhaps it began its existence 6 billion years ago, deep in the core of a massive star. At the center of that star, temperatures reached 15 million degrees. The pressure was so intense that lighter elements fused together, building heavier and heavier elements step by step. Hydrogen fused into helium. Helium fused with helium to create beryllium, then more helium to create carbon. Our carbon atom, newly forged, resided in that stellar core for millions of years. The star shone brilliantly, powered by the fusion reactions happening at its heart. But massive stars burn through their fuel quickly, cosmically speaking. After perhaps 10 million years, the star had fused elements all the way up to iron in its core. The iron core grew until it could no longer support itself. In less than a second, it collapsed. The collapse released energy so stupendous that it sent a shockwave racing through the star's outer layers. The shockwave hit those outer layers, traveling at a significant fraction of the speed of light, compressing and heating the material to unimaginable temperatures. Our carbon atom, sitting in one of those outer layers, suddenly found itself in the midst of a supernova explosion. In the violence of that explosion, the carbon atom was flung into space at tremendous velocity. It traveled through the interstellar medium for hundreds of millions of years, drifting as part of a slowly expanding cloud of stellar debris. This cloud, enriched with heavy elements from the supernova, eventually encountered other clouds of gas and dust in the galaxy. Gravity slowly pulled these clouds together. Perhaps 5 billion years ago, a dense region of the cloud began to collapse in on itself, forming what would become our solar system. Our carbon atom was part of this collapsing cloud. Some of the material fell into the center, forming the sun. But our carbon atom ended up in the disk of gas and dust swirling around the young sun. In this disk, dust particles bumped into each other and stuck together. Tiny grains became pebbles, pebbles became boulders, boulders became planetesimals, and planetesimals, through countless collisions over millions of years, became planets. Our carbon atom became part of one of these planetesimals, which eventually became part of Earth. For billions of years, that carbon atom was locked in rock, deep beneath Earth's surface. Then, perhaps through volcanic activity, it made its way toward the surface. Eventually, weathering and erosion broke down the rock, and the carbon atom became part of the soil. A plant, through photosynthesis, captured carbon dioxide from the air and incorporated carbon into its structure. But our atom remained in the soil. Time passed. Perhaps that carbon atom spent time in different rocks, in the ocean as dissolved carbon dioxide, in the shells of marine organisms that lived and died and drifted to the seafloor to become limestone. Perhaps it was buried, heated, compressed, transformed through geological processes, then uplifted and exposed again through plate tectonics. Eventually, perhaps just recently, that carbon atom became part of a plant you ate. Your digestive system broke down the plant's molecules, and the carbon atom was absorbed into your bloodstream. Your body incorporated it into a molecule in one of your cells, perhaps part of a protein or a fat molecule or even a sugar molecule being broken down for energy. And now it's part of you, at least temporarily. This journey from the heart of an ancient star to your body took billions of years and involved processes spanning the full range of physical phenomena, from nuclear fusion to chemistry to biology. And this isn't unique to one special carbon atom. Every carbon atom in your body has a similar story, though the details differ. Every oxygen atom, every nitrogen atom, every atom heavier than hydrogen has traveled an epic journey through space and time. When life emerged on Earth, perhaps 3.8 billion years ago, it built itself from the available atoms. The first simple cells incorporated carbon, hydrogen, oxygen, nitrogen, phosphorus, and other elements into their structures. As life evolved and diversified, it continued to use these stellar gifts, creating ever more complex molecular architectures. Those first living cells were themselves remarkable assemblies of atoms. They had membranes to separate their interior from the environment, made of lipid molecules assembled from carbon, hydrogen, and oxygen. They had proteins that catalyzed chemical reactions, long chains of amino acids, themselves built from carbon, nitrogen, oxygen, hydrogen, and sometimes sulfur. They had genetic material, perhaps RNA initially, storing information in sequences of nucleotides. All of this molecular machinery, all of these intricate structures that could capture energy, grow, repair themselves, and reproduce, emerged from atoms whose properties are determined by the number of protons in their nuclei and the quantum mechanical behavior of their electrons. Life is chemistry, chemistry is physics, and physics is ultimately about the behavior of atoms and the particles that compose them. Fast forward to today, to you, lying comfortably in your bed. The carbon in your DNA was created inside a star that died before our solar system existed. That carbon atom might have been part of that star for millions of years, fusing and refusing with other elements in the stellar core. Then came the supernova, the explosive ending, and that atom was flung into the depths of space. It drifted for perhaps hundreds of millions of years before becoming part of the cloud that formed our solar system. It might have spent time in comets or asteroids before eventually becoming part of Earth. It might have been in rocks, in oceans, in ancient organisms, in plants and animals and other people before finally becoming part of you. The iron in your blood, crucial for carrying oxygen throughout your body, was also created in a massive star. Iron forms in the final stages of a star's life, just before it goes supernova. The atoms of iron in your hemoglobin have witnessed the death of a star, the birth of a solar system, and the entire history of Earth. Even the calcium in your bones has a cosmic origin. When you were a child, your body took calcium atoms from your food and incorporated them into your growing skeleton. Those atoms might have been in milk from a cow that ate grass containing calcium from the soil. That calcium in the soil might have weathered from rocks over millions of years. And those rocks formed when Earth was young, from material in the solar nebula, from atoms created in ancient stellar explosions. The oxygen you breathe with every breath was also created in stars, specifically in stars much larger than our Sun. These massive stars fused helium into carbon, and then carbon with helium to create oxygen. When these stars died, they released their oxygen into space, where it eventually became part of Earth's atmosphere. Every oxygen atom you inhale has cycled through countless organisms before reaching your lungs. There's a beautiful calculation that some physicists have done regarding the breath of famous historical figures. Take someone like William Shakespeare, who lived about 400 years ago. In his lifetime, Shakespeare took countless breaths, perhaps 400 million or so. Each breath contained about 10 to the 22nd power molecules. These molecules, containing hydrogen, oxygen, nitrogen, and carbon atoms, were exhaled into the air. Over the 4 centuries since his death, these molecules have mixed thoroughly throughout Earth's atmosphere. When you breathe in right now, the odds are extraordinarily high that you're inhaling atoms that were once part of Shakespeare's breath. In fact, with each breath you take, you're probably breathing in hundreds or even thousands of atoms that were part of Shakespeare, Julius Caesar, Cleopatra, or any other historical figure you can think of. You're breathing atoms that were part of dinosaurs, ancient trees, the first fish to crawl onto land, the first humans to walk upright. This recycling of atoms connects all life on Earth into a single, interwoven story. The atoms in your body have been part of countless other organisms. They've been in bacteria, plants, animals, other humans. They've traveled around the world many times over, carried by wind and water, by migrations and meals, by the endless cycles of life, death, and renewal. But the connection goes deeper than just life on Earth. Those atoms came from stars scattered across our galaxy. The Milky Way contains hundreds of billions of stars, and over its history, countless stars have lived and died, each one contributing to the chemical enrichment of the galaxy. The atoms in your body might come from stars that were anywhere in the galaxy, from the dense core to the spiral arms stretching out into space. And even more remarkably, some elements weren't created in stars at all, but in the collision of neutron stars, the incredibly dense remnants left behind after certain supernovae. When 2 neutron stars spiral into each other and collide, they create conditions even more extreme than a supernova. In these collisions, elements like gold, platinum, and uranium are formed. So the gold in jewelry, in electronics, perhaps even in trace amounts in your body, was created not in a stellar furnace but in the apocalyptic merger of 2 collapsed stellar cores. As you rest there, contemplating these cosmic connections, you might feel a sense of perspective settling over you. The stresses and worries of your daily life, while real and important to you, are occurring on a timescale of hours, days, and years. But the atoms of your body have been on a journey measured in billions of years. They've witnessed the birth and death of stars, the formation of galaxies, the creation of planets, and the emergence of life. You are a temporary arrangement of ancient matter, a brief pattern in the endless dance of atoms through time and space. This knowledge doesn't diminish you, quite the opposite. It reveals your intimate connection to the cosmos. You are not separate from the universe, observing it from outside. You are the universe experiencing itself, matter organized in such a way that it can look back at its own origins and marvel at the journey. The atoms that make you possible were forged in the hearts of dying stars billions of years ago. They will continue their journey long after you're gone, becoming part of other patterns, other lives, other stories. For now, though, they're arranged in the magnificent complexity that is you, lying peacefully in the dark, breathing the recycled breath of all history, made of the dust of ancient stars. The quantum dance. Now let's drift into the truly strange and beautiful realm of quantum mechanics, where atoms behave in ways that seem to defy common sense, yet follow mathematical laws of profound elegance. This is where the story of atoms becomes almost dreamlike, and perhaps that's fitting, given that you're preparing for sleep, where your own consciousness enters territories equally mysterious. Earlier, we mentioned that electrons don't orbit the nucleus like planets around a sun. This deserves deeper exploration because it touches on one of the most fundamental shifts in human understanding that occurred in the 20th century. When physicists first discovered electrons in the late 1800s, they naturally tried to understand them using the physics they knew, the classical physics that describes balls rolling down hills, pendulums swinging, and planets orbiting stars. But electrons refused to behave according to classical rules. Experiments kept revealing puzzling properties. Sometimes electrons acted like particles, tiny bullets of matter with definite positions and paths. Other times they acted like waves, spreading out and interfering with themselves in ways that only waves can do. This wave-particle duality baffled scientists for years. In 1926, an Austrian physicist named Erwin Schrödinger developed a mathematical equation that could describe the behavior of electrons in atoms. Rather than predicting a definite position for an electron, Schrödinger's equation yields what we call a wave function, a mathematical object that describes the probability of finding the electron in different regions around the nucleus. Imagine holding a globe in your hands in a dark room. Now imagine that instead of the globe being solid, it's a cloud with varying density. In some regions, the cloud is thick and opaque. In others, it's thin and wispy. This cloud represents the probability of finding an electron. Where the cloud is dense, the electron is likely to be. Where it's thin, the electron is unlikely to be found. These probability clouds, which physicists call orbitals, have distinct shapes depending on the energy state of the electron. The simplest orbital, called an s orbital, is spherical, surrounding the nucleus in all directions equally. Imagine a fuzzy ball of probability. The next type, called p orbitals, look like figure eights or dumbbells with the nucleus at the center. Then come d orbitals and f orbitals, with increasingly complex and beautiful shapes. But here's the truly mysterious part. Before you observe an electron, before you measure its position, it doesn't have a definite location. It's not that we simply don't know where it is. It genuinely doesn't have a specific position. The electron is described by its wave function, which spreads out across space. Only when you perform a measurement does the electron appear to suddenly be in one place. This is called the collapse of the wave function, and despite nearly a century of debate, physicists still argue about what this actually means. This peculiarity is related to the famous uncertainty principle, discovered by Werner Heisenberg in 1927. The principle states that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you determine one, the less precisely you can know the other. This isn't a limitation of our measuring tools. It's a fundamental feature of reality at the quantum scale. Think about it like this. To see where an electron is, you need to bounce light off it. But light comes in packets called photons, and when a photon hits an electron, it gives the electron a kick, changing its momentum. The shorter the wavelength of light you use to get a more precise position measurement, the more energy the photon has, and the bigger kick it gives the electron, making its momentum more uncertain. There's no way around this. It's built into the fabric of quantum mechanics. This uncertainty isn't just an abstract philosophical curiosity. It has profound physical consequences. It's part of what keeps atoms stable. In classical physics, an electron orbiting a nucleus should gradually radiate energy and spiral into the nucleus, causing the atom to collapse. But quantum mechanics says that confining an electron to a smaller region around the nucleus would mean knowing its position more precisely, which would make its momentum more uncertain, which would actually increase its energy. This quantum pressure, arising from the uncertainty principle, is part of what keeps atoms from collapsing. Electrons in atoms can only occupy certain discrete energy levels, like steps on a staircase rather than a smooth ramp. An electron in a lower energy orbital is more tightly bound to the nucleus. To move to a higher energy orbital, the electron must absorb exactly the right amount of energy. This energy often comes in the form of a photon of light. Similarly, when an electron drops from a higher energy level to a lower one, it emits a photon with energy exactly equal to the difference between the two levels. This is why atoms emit and absorb light at specific wavelengths. Each element has a unique set of possible electron energy levels, and therefore a unique set of wavelengths it can emit or absorb. This spectral signature is like a fingerprint. By looking at the light coming from a distant star, astronomers can determine exactly which elements are present in that star, even though the star might be thousands or millions of light years away. The quantum nature of atoms also gives rise to a strange property called superposition. Before a measurement is made, a quantum system can exist in multiple states simultaneously. That electron we've been discussing, it's not just in one position in its orbital. It's effectively in all possible positions allowed by its wave function, at least until a measurement causes it to appear in one location. Schrödinger famously illustrated the strangeness of this with a thought experiment involving a cat in a box, supposedly in a superposition of being both alive and dead until the box is opened. While this thought experiment has led to much philosophical debate, the principle it illustrates applies genuinely to atoms and subatomic particles. Another quantum property, called entanglement, allows particles that have interacted to remain connected in ways that transcend space. Measure a property of one particle, and you instantaneously affect the possibilities for the other particle, even if they're on opposite sides of the universe. Einstein famously called this spooky action at a distance and was deeply uncomfortable with it, yet experiment after experiment has confirmed that entanglement is real. These quantum effects are not just theoretical abstractions. They have practical applications that touch your life every day. The transistors in your phone and computer work because of quantum tunneling, a phenomenon where particles can pass through barriers that classical physics says should be impenetrable. The laser that reads the disk in your computer uses light produced by electrons jumping between energy levels in atoms. Medical imaging techniques like PET scans rely on antimatter, a quantum prediction that turns out to exist in reality. As you lie there in the darkness, the quantum world continues its probabilistic dance. Electrons in the atoms of your body are not in fixed positions but exist in clouds of probability around nuclei. These electrons can only be in certain allowed energy states, and they're constantly absorbing and emitting photons, participating in the chemical reactions that power your metabolism, your thoughts, your dreams. The boundary between the quantum world and the classical world we experience in everyday life remains fuzzy and mysterious. Quantum effects seem to wash out when large numbers of particles interact, giving rise to the solid, predictable world of chairs and tables and beds. But the quantum realm is always there, underlying everything, a world of probability and uncertainty that nevertheless gives rise to the stable patterns we call matter. In a way, you're built on uncertainty. Every atom in your body, every electron dancing in its probability cloud, embodies the quantum principle that exact prediction is impossible, that reality at its most fundamental level remains probabilistic. Yet from this uncertainty emerges the beautiful stability of atoms, the reliability of chemistry, the predictable processes that keep you alive. Order arising from chaos, stability from uncertainty, life from the quantum dance of particles. Consider the simple act of vision, which you might use to read these words or might forgo as your eyes stay closed in the darkness. When light enters your eye, photons strike molecules called rhodopsin in the cells of your retina. These photons, quantum packets of electromagnetic energy, cause electrons in the rhodopsin molecules to jump to higher energy states. This triggers a cascade of chemical reactions that eventually sends a signal to your brain. Everything in this process, from the absorption of photons to the movement of electrons to the breaking and forming of chemical bonds, is governed by quantum mechanics. Your ability to see exists because of the quantized nature of energy, because electrons can only exist in certain states, because atoms absorb and emit light at specific wavelengths determined by their quantum structure. The same is true for your sense of smell. When molecules from, say, a flower drift into your nose, they bind to receptor proteins. This binding changes the shape of the proteins slightly, which changes the energy states of electrons in certain atoms in the protein. This triggers a signal. Your brain interprets this signal as a particular smell. The specificity of smell, the fact that a rose smells different from a jasmine flower, comes down to the precise shapes of molecules, which are determined by how atoms bond, which is itself determined by the quantum mechanical behavior of electrons. Your sense of taste works similarly. Molecules in food interact with taste receptors on your tongue. Sweet molecules fit into sweet receptors, bitter molecules into bitter receptors, and so on. These interactions change the electronic states of atoms in the receptor proteins, triggering signals to your brain. The quantum world underlies your every sensory experience. Even your thoughts, the words passing through your mind right now as you listen or read, arise from quantum processes. Neurons in your brain communicate by sending electrical signals along their length and then releasing neurotransmitter molecules at their endings. These molecules drift across the tiny gap between neurons, bind to receptors on the next neuron, and trigger a new electrical signal. All of this involves the movement of charged particles, electrons, and ions, whose behavior is ultimately quantum mechanical. The stability of atoms themselves, which we've touched on, deserves more wonder. In classical physics, an accelerating charged particle radiates electromagnetic energy. An electron moving in a circle around a nucleus would be constantly accelerating, because its direction is constantly changing. It should radiate away its energy and spiral into the nucleus in a tiny fraction of a second. Atoms should not exist. Matter should not exist. The universe should have collapsed into a uniform fog of positive and negative charges shortly after the Big Bang. But quantum mechanics saves the day. Electrons don't follow definite paths. They exist in orbitals, quantum states that are solutions to Schrödinger's equation. These orbitals are stable. An electron in a ground state orbital has nowhere to go, no lower energy state to drop to. It just persists there, its probability cloud unchanging with time, as long as nothing disturbs it. This quantum stability is what makes matter possible, what makes your existence possible. There's also something called quantum tunneling, where particles can pass through barriers that classical physics says they shouldn't be able to penetrate. This happens because particles are described by wave functions that can extend beyond classical boundaries. There's a small but non-zero probability that a particle can be found on the other side of a barrier, even if it doesn't have enough energy to go over the barrier in the classical sense. Quantum tunneling is not just theoretical. It's essential to how the sun works. The temperature and pressure at the sun's core are enormous, but even so, they're not quite enough to overcome the electrical repulsion between protons using just classical physics. Quantum tunneling allows protons to get close enough to fuse together despite the repulsion. Without tunneling, the sun wouldn't shine, Earth would be frozen, and life would never have emerged. Tunneling also happens in your body. Some enzymes, the biological catalysts that make biochemical reactions possible, work partly through quantum tunneling. Hydrogen atoms, or more precisely their nuclei, which are single protons, can tunnel through energy barriers in enzyme active sites. This allows reactions to proceed faster than they otherwise could, fast enough to sustain life's processes. Perhaps there's even quantum effects in consciousness itself, though this remains highly speculative and controversial. Some researchers have proposed that quantum processes in the microtubules of neurons might play a role in how the brain generates conscious experience. Others are skeptical, arguing that the brain is too warm and wet for quantum effects to persist in a meaningful way. The truth remains unknown, an open question at the frontier of neuroscience and physics. Perhaps there's a metaphor here for consciousness itself, for the strange way your sense of self emerges from the coordinated firing of billions of neurons, themselves made of molecules, themselves made of atoms following quantum rules. You are an impossibly complex pattern of quantum interactions, giving rise to something that can ponder its own nature, can feel wonder at the universe, can choose to lie down peacefully and let sleep wash over you like a gentle tide. The early quest to understand, The path to understanding atoms was long and winding, filled with brilliant insights, false starts, and occasional leaps of intuition that turned out to be remarkably prescient. Let's drift back through history, watching as humans gradually piece together the atomic nature of reality, each generation building on the discoveries of the previous one. The ancient Greek philosopher Democritus, living around 400 BC, proposed that matter was made of tiny, indivisible particles he called atomos. He reasoned that if you kept cutting a piece of matter into smaller and smaller pieces, you must eventually reach a point where you could cut no further, where you'd reach the fundamental unit. He imagined these atoms as solid, eternal, and unchanging, differing only in shape and size. Different substances, he proposed, were made of different arrangements of these fundamental particles. Democritus's idea was purely philosophical, based on logic rather than experiment. His contemporary Aristotle disagreed, arguing instead that matter was continuous and infinitely divisible, made up of combinations of 4 elements: earth, water, air, and fire. Aristotle's views dominated Western thought for nearly 2,000 years, partly because he was considered an unquestionable authority and partly because without experimental methods, there was no way to test these competing ideas. The atomic theory lay dormant until the early 19th century, when chemistry began to emerge as a rigorous experimental science. Chemists noticed regular patterns in how substances combined. When hydrogen and oxygen combine to form water, they always do so in a specific ratio by weight. When carbon burns in oxygen to form carbon dioxide, there's again a fixed ratio. These and other observations suggested that matter might indeed come in discrete units that combine in whole number ratios. In 1803, an English chemist named John Dalton published the first modern atomic theory. Based on careful measurements and observations, Dalton proposed that each element is made of identical atoms, that atoms of different elements have different masses, and that chemical reactions involve the rearrangement of these atoms, not their creation or destruction. His theory explained the observed patterns in chemistry and sparked a revolution in how scientists understood matter. Dalton's atoms were still imagined as solid, indivisible spheres, but his theory provided a framework that later scientists could build upon and refine. Throughout the 1800s, chemists continued to measure and catalog the properties of elements, eventually organizing them into the periodic table, a chart that revealed surprising patterns and relationships between elements. The next breakthrough came in 1897, when British physicist J.J. Thomson was experimenting with cathode rays, mysterious rays that appeared when electricity was passed through a glass tube with most of the air removed. By studying how these rays were deflected by electric and magnetic fields, Thomson concluded that they must be streams of tiny, negatively charged particles much lighter than any atom. He had discovered the electron. This discovery shattered the idea of atoms as indivisible. If atoms contained electrons, they must have internal structure. Thomson proposed what came to be called the plum pudding model. He suggested that an atom was like a sphere of positive charge with electrons embedded in it like raisins in a pudding. This model had electrons as part of the atom but didn't really explain much about atomic structure or behavior. The crucial experiment that revealed the true structure of atoms came in 1909, though its implications weren't fully understood until a couple of years later. A New Zealand physicist named Ernest Rutherford, working at the University of Manchester in England, designed an experiment to probe the structure of atoms using alpha particles. Alpha particles are helium nuclei, consisting of 2 protons and 2 neutrons bound together. They're emitted by certain radioactive materials like radium. Rutherford and his colleagues Ernest Marsden and Hans Geiger took a thin film of gold foil, about 400 atoms thick, and fired alpha particles at it. According to Thomson's plum pudding model, the alpha particles should have passed straight through with only minor deflections, like bullets passing through soft tissue. Most of the alpha particles did indeed pass through the foil with little or no deflection, exactly as expected. But to everyone's astonishment, a tiny fraction of the alpha particles, perhaps 1 in 8,000, bounced back at large angles. Some even came straight back toward the source. Rutherford later remarked that this was as surprising as if you fired a battleship shell at tissue paper and it bounced back and hit you. This result could only mean one thing. The positive charge and most of the mass of the atom were concentrated in a tiny region at its center, a region Rutherford called the nucleus. Most of the alpha particles passed through the empty space of the atom, but the rare ones that came near the nucleus were deflected by its concentrated positive charge. By analyzing the scattering pattern, Rutherford could calculate that the nucleus was about 10,000 times smaller than the atom itself. This was the birth of the nuclear model of the atom, the model we still use today in its basic form. An atom consists of a tiny, dense, positively charged nucleus surrounded by a comparatively vast region in which electrons reside. Rutherford had discovered that atoms are mostly empty space, a fact that still seems counterintuitive when you're lying on your very solid bed. But the nuclear model presented a problem. According to classical physics, electrons orbiting a nucleus should continuously radiate energy and spiral into the nucleus in a fraction of a second. Atoms should be unstable, yet clearly they're not. This paradox pointed to the need for a new kind of physics. A young Danish physicist named Niels Bohr, working with Rutherford in 1913, proposed a solution. He suggested that electrons could only occupy certain specific orbits around the nucleus, and that while in these orbits they didn't radiate energy. Electrons could jump between orbits by absorbing or emitting photons, but they couldn't exist between these allowed states. This quantization of electron orbits, while somewhat arbitrary, explained many properties of atoms, particularly the discrete wavelengths of light they emit and absorb. Bohr's model was a major step forward, but it was also clearly incomplete. It worked well for hydrogen, the simplest atom, but struggled with more complex atoms. It couldn't explain why electrons stayed in their orbits or why only certain orbits were allowed. These questions would have to wait for the development of quantum mechanics in the 1920s, which we've already touched upon. As you rest there, perhaps starting to feel the pull of sleep, consider the remarkable journey of human understanding. From the ancient Greeks' logical speculations to the precise experiments of modern physics, humanity gradually uncovered the atomic nature of reality. Each scientist built on the work of those who came before, sometimes confirming earlier ideas, sometimes overturning them completely. The story of atomic discovery is also a reminder of the power of curiosity and persistence. Many of these scientists worked with primitive equipment by today's standards. They couldn't see atoms directly. They had to infer their existence and properties from indirect evidence, from patterns in how substances combined, from the deflection of invisible particles, from the wavelengths of light emitted by hot gases. Yet, through careful reasoning and clever experimentation, they reconstructed the hidden architecture of matter. And their discoveries weren't just academic. Understanding atoms opened the door to technologies that have transformed human civilization. Chemistry became a mature science, allowing us to synthesize new materials and medicines. Electronics emerged from understanding how electrons move through different materials. Nuclear technology, for better and worse, arose from our growing knowledge of atomic nuclei. The path from Dalton's theory to practical applications took many decades and involved countless researchers. Chemists learned to synthesize new compounds, creating medicines that could cure diseases, dyes that could color fabrics, fertilizers that could increase crop yields. The chemical industry grew into one of the most important sectors of the modern economy, all based on understanding how atoms combine. The late 19th century saw remarkable progress in understanding the behavior of matter. Scientists studied gases and developed the kinetic theory, which explained gas pressure and temperature in terms of atoms and molecules in constant motion. They studied solutions and crystallization and developed laws describing how substances dissolve and precipitate. They studied acids and bases and electrochemistry. All of this work was done without directly observing atoms. Scientists inferred their existence from the patterns they observed in chemical reactions and physical properties. It was like being blind but figuring out the shape of objects by touching them, by feeling their effects. The evidence for atoms accumulated until their existence became undeniable, even to skeptics. At the same time, physicists were discovering that matter could interact with electromagnetic radiation in interesting ways. When certain materials were heated until they glowed, they emitted light with specific wavelengths characteristic of the elements they contained. Astronomers could look at the light from distant stars and, by analyzing which wavelengths were present or absent, determine what elements the stars contained. This spectroscopy revealed that the universe was made of the same elements found on Earth. But why did elements emit light at specific wavelengths? The answer would require understanding the internal structure of atoms, which would come with Thomson's discovery of the electron. Before Thomson, atoms were thought to be the smallest units of matter, truly indivisible. His discovery that atoms contain smaller, charged particles revolutionized physics. Thomson's experiments with cathode rays involved passing electricity through tubes with most of the air pumped out. In these tubes, mysterious rays appeared, traveling from the cathode or negative electrode to the anode or positive electrode. When these rays hit a fluorescent screen at the end of the tube, they caused it to glow. Thomson found that these cathode rays could be deflected by magnetic fields and by electric fields. By carefully measuring how much the rays deflected under different field strengths, he could calculate the ratio of charge to mass for the particles making up the rays. He found that this ratio was much larger than for any known ion, meaning the particles were either very highly charged or very light or both. Through further experiments, Thomson determined that the particles all had the same charge, regardless of what material the cathode was made from or what residual gas remained in the tube. This universality suggested that these particles, which he called corpuscles but we now call electrons, were a fundamental constituent of all matter. The discovery of the electron won Thomson the Nobel Prize in Physics in 1906, and it marked the beginning of atomic physics as a distinct field. If atoms contained electrons, and if electrons were negatively charged, atoms must also contain positive charge to balance the negative charge and make atoms overall neutral. But how was this positive charge arranged? Thomson proposed his plum pudding model, but even as he did so, others were developing better experimental techniques to probe the structure of atoms. Rutherford's experiments with alpha particles and radioactivity would soon reveal that the positive charge was concentrated in a tiny nucleus, not spread throughout the atom as Thomson had proposed. But we're getting ahead of ourselves. We haven't yet reached the heart of our story. How scientists learned to split the atom, to break apart the nucleus itself and release the tremendous energy locked within. That discovery would come from a combination of theoretical insight and experimental ingenuity, and it would change the world in profound and complicated ways. But for now, let your mind rest on these early explorers of the atomic realm, these pioneers who first mapped the invisible landscape that underlies all of reality. The birth of nuclear physics. Ernest Rutherford wasn't content with just discovering the nucleus. He wanted to understand it, to probe its properties, to discover what it was made of and how it behaved. In the years following his gold foil experiment, he turned his attention to bombarding different elements with alpha particles to see what would happen. In 1919, Rutherford made another groundbreaking discovery. He was firing alpha particles at nitrogen gas, and he detected particles being emitted that behaved like hydrogen nuclei. Somehow, the impact of the alpha particles was causing nitrogen nuclei to eject these hydrogen nuclei. Rutherford had achieved the first artificial transmutation of one element into another, turning nitrogen into oxygen by knocking out a hydrogen nucleus. This hydrogen nucleus, which Rutherford eventually named the proton, turned out to be a fundamental constituent of all atomic nuclei. He had discovered that the nucleus was not a uniform blob but had internal structure, containing discrete particles. The number of protons in a nucleus determined what element it was. Hydrogen had 1 proton, helium had 2, carbon had 6, oxygen had 8, and so on. But there was a puzzle. The masses of atomic nuclei didn't match what you'd expect if they only contained protons. A helium nucleus, for instance, has 2 protons, so you'd expect it to have about twice the mass of a hydrogen nucleus with 1 proton. But actually, it has about 4 times the mass. Something else was in there, contributing mass but not electrical charge. Physicists hypothesized the existence of another particle in the nucleus electrically neutral, with about the same mass as a proton. They called this hypothetical particle the neutron. But proving it existed was challenging because it carried no charge, making it hard to detect. Uncharged particles don't leave tracks in the detection devices of that era, which mostly relied on charged particles ionizing gas atoms as they passed through. The search for the neutron continued through the 1920s. Various experiments produced confusing results that seemed to hint at something, but the interpretation was unclear. Then, in 1932, a crucial experiment was performed by James Chadwick, a British physicist working at the Cavendish Laboratory at Cambridge University, where Rutherford was now director. Chadwick was studying a peculiar radiation produced when beryllium was bombarded with alpha particles. Initially, researchers thought this radiation was high-energy gamma rays, a form of electromagnetic radiation. But Chadwick showed that this couldn't be right. The radiation could knock protons out of paraffin wax with considerable energy, far more than gamma rays of that energy could transfer. By careful measurements and calculations, Chadwick demonstrated that the radiation consisted of neutral particles with about the same mass as protons. These were Rutherford's hypothesized neutrons. Their neutrality explained why they hadn't been directly detected earlier. Their presence in nuclei explained the mass discrepancy. Atoms were made of protons, neutrons, and electrons, a picture that has remained fundamentally correct. With the discovery of the neutron, the basic structure of the atom was finally understood. The nucleus contained protons and neutrons bound together by the strong nuclear force. The number of protons determined the element. Different isotopes of the same element had the same number of protons but different numbers of neutrons. Electrons orbited the nucleus in quantum orbitals, their negative charge balancing the positive charge of the protons in a neutral atom. But physicists noticed something interesting about the neutron. Unlike protons, which repel each other electrically, neutrons don't repel or attract protons through the electromagnetic force. But they do interact with protons and with other neutrons through the strong force. In fact, neutrons serve as a kind of nuclear glue. The more protons you have in a nucleus, the more they repel each other electrically. Adding neutrons provides additional strong force attraction without adding more electrical repulsion, helping to hold larger nuclei together. This explained why heavy elements have proportionally more neutrons than light elements. Hydrogen typically has no neutrons, just a single proton. Helium has 2 protons and 2 neutrons. Carbon has 6 protons and 6 neutrons. But uranium, with 92 protons, has 146 neutrons in its most common isotope. The extra neutrons are needed to stabilize the nucleus against the electrical repulsion of all those protons. Even so, very heavy nuclei are inherently unstable. The electrical repulsion between protons grows stronger as you add more protons, while the strong force only acts over very short ranges. Eventually, you reach elements so heavy that no number of neutrons can keep them stable indefinitely. These radioactive elements spontaneously decay, transforming into lighter elements by emitting particles and energy. Rutherford's laboratory at the Cavendish became a hub of nuclear physics research in the early 1930s. It was an exciting time with new discoveries coming rapidly. Scientists were learning to produce radioactive isotopes artificially, studying how particles behaved when fired at various targets, and developing new experimental techniques. Among the researchers at the Cavendish were John Cockcroft and Ernest Walton, who were working on a different approach to probing the nucleus. Instead of relying on naturally occurring alpha particles from radioactive materials, they wanted to artificially accelerate particles to high energies and use them as probes. They built a device that could accelerate protons using high voltages, essentially creating a beam of high-energy protons on demand. The idea was simple in principle but challenging in practice. Apply a high voltage between 2 electrodes in a vacuum tube, and charged particles will be accelerated from one electrode to the other. But getting voltages high enough to give protons sufficient energy to overcome the electrical repulsion of nuclei and penetrate them was difficult with the technology of the time. Cockcroft and Walton managed to achieve voltages of several 100,000 volts, creating a beam of protons with energies high enough to induce nuclear reactions. In April 1932, just weeks after Chadwick's discovery of the neutron, they performed a historic experiment. They fired their beam of accelerated protons at a target made of lithium, element number 3. The result was extraordinary. When the protons struck lithium nuclei, the nuclei split apart, producing 2 alpha particles. Lithium-7 plus a proton turned into 2 helium-4 nuclei. For the first time, a nuclear reaction had been induced entirely by artificial means. Cockcroft and Walton had split the atom. This phrase, splitting the atom, became famous, though it's worth clarifying what it meant in this context. They weren't splitting atoms in the sense of dividing electrons from nuclei. They were splitting atomic nuclei, breaking them apart into smaller nuclei. It was a nuclear reaction, not a chemical reaction. Moreover, they verified a prediction of Einstein's special theory of relativity. Before the reaction, they had a lithium nucleus and a proton. After, they had 2 alpha particles. But if you carefully measured the masses involved, the total mass of the 2 alpha particles was slightly less than the total mass of the lithium and proton. Where did the missing mass go? Einstein's famous equation E=mc² gave the answer. Mass and energy are interchangeable. The missing mass had been converted into energy, appearing as the kinetic energy of the 2 alpha particles flying apart. This was direct experimental confirmation that mass could be converted into energy in nuclear reactions, a principle that would have profound implications. Cockcroft and Walton's achievement, coming in that remarkable year of 1932 alongside the discovery of the neutron and the positron, opened up a new field of experimental nuclear physics. It demonstrated that particle accelerators could be powerful tools for studying atomic nuclei. In the decades that followed, accelerators would grow larger and more powerful, eventually becoming the massive facilities like CERN's Large Hadron Collider that probe the fundamental nature of matter and energy. As you lie there, feeling perhaps the first wisps of dream beginning to intrude on waking thought, you might appreciate the remarkable precision and ingenuity of these early nuclear physicists. They were working with particles they couldn't see, with energies and masses they could only infer from careful measurements, with equipment they often built themselves in university laboratories. Yet they mapped out the structure of the atomic nucleus and discovered fundamental laws of nature. Their work required both theoretical insight and experimental skill. They had to understand the physics well enough to predict what should happen in their experiments, but they also had to be clever enough to design experiments that could actually test those predictions with the limited technology available. And they had to be persistent, running experiment after experiment, troubleshooting equipment failures, carefully analyzing data, gradually building up a coherent picture of the nuclear world. But Cockcroft and Walton's splitting of lithium nuclei, while historic, was not nuclear fission in the sense we usually mean. The lithium nucleus split cleanly into 2 roughly equal parts, but this kind of reaction couldn't sustain itself or release large amounts of energy on a practical scale. The discovery that would truly change the world was still to come, and it would emerge from a different series of experiments, using a different element, and revealing a phenomenon that even the most brilliant physicists of the time initially failed to understand: the discovery of nuclear fission. The path to discovering nuclear fission was winding and involved scientists across Europe working sometimes together, sometimes in competition, sometimes unaware of the significance of their own results. It's a story of brilliant experimental work, inspired theoretical insight, and the dark shadow of rising fascism that would eventually scatter many of these researchers across the globe. By the mid-1930s, scientists had been bombarding uranium, the heaviest naturally occurring element, with neutrons to see what would happen. Uranium has 92 protons, and physicists wondered if they could create even heavier elements by adding neutrons to uranium nuclei, which might then undergo radioactive decay that would transform neutrons into protons, creating elements 93, 94, and beyond. An Italian physicist named Enrico Fermi led one of the groups pursuing this research. He found that when he bombarded uranium with neutrons, he got a confusing array of radioactive products. He thought he might have created new elements beyond uranium, which he called transuranics. But the chemistry was puzzling. The products didn't behave quite like you'd expect for elements heavier than uranium. In Germany, a team of chemists and physicists were also studying neutron bombardment of uranium. The team included Otto Hahn, a gifted chemist, Fritz Strassmann, a younger colleague, and Lise Meitner, a brilliant physicist who had collaborated with Hahn for decades. They too found confusing results when they analyzed the products of neutron bombardment. But then history intervened. Lise Meitner was Jewish, and in 1938, Nazi Germany annexed Austria, where Meitner had been born. Though she was working in Germany and had converted to Christianity years earlier, this didn't protect her from Nazi racial laws. She fled Germany in July 1938, eventually making her way to Sweden, where she found refuge and a position at a research institute. Despite being separated from her longtime collaborators, Meitner stayed in touch with Hahn through letters. In December 1938, Hahn and Strassmann performed a careful chemical analysis of the products from neutron bombardment of uranium. They found something completely unexpected. Among the products was barium, element number 56. This made no sense at all according to the prevailing understanding of nuclear reactions. Barium has 36 fewer protons than uranium. The known types of radioactive decay, alpha decay and beta decay, could change an element's atomic number by at most 2 in one step. There was no sequence of known decays that could turn uranium into barium. Yet the chemistry was unambiguous. Barium was definitely present. Hahn wrote to Meitner describing the perplexing result, asking for her thoughts. He was considering publishing the finding but worried about how it could be explained. Meitner, despite the trauma of her recent flight from Germany, focused her formidable intellect on the puzzle. It happened that Meitner's nephew, Otto Frisch, was also a physicist working in Copenhagen at the Institute of Niels Bohr. During Christmas 1938, Frisch visited his aunt in Sweden. They went for a walk in the snow, discussing the barium mystery. As they talked, Meitner had an insight. What if the uranium nucleus wasn't just ejecting a particle or two? What if the whole nucleus was splitting apart into too much lighter nuclei? If a uranium nucleus split roughly in half, one of the products might indeed be barium or something close to it. But why would a nucleus split in this way? Meitner applied her understanding of nuclear physics. Bohr had recently proposed a model of the nucleus as being somewhat like a liquid drop, held together by surface tension created by the strong force. If a uranium nucleus absorbed a neutron and became excited, it might start to oscillate like a wobbling water droplet. If the oscillations became violent enough, the nucleus might stretch out into an elongated shape. At some point, the electrical repulsion between the two ends of this elongated nucleus could overcome the strong force trying to hold it together. The nucleus would pinch in the middle and split into two fragments like a water droplet breaking in two. Meitner and Frisch did some quick calculations there in the Swedish snow. If a uranium nucleus split into two lighter nuclei, there would be a difference in mass. The two product nuclei together would weigh slightly less than the original uranium nucleus plus the neutron. That missing mass would be converted into energy according to Einstein's E equals mc squared. How much energy? About 200 million electron volts per fission. This was an enormous amount of energy by atomic standards, about 50 million times more energy than you'd get from a chemical reaction involving a single atom. The energy would appear as the kinetic energy of the two fragments flying apart at tremendous speed, plus some gamma rays and additional neutrons that might also be emitted. They wrote up their insight in a short paper, which Frisch submitted to the journal Nature in January 1939. Frisch suggested naming the process fission by analogy with biological cell division, or binary fission. The paper was published on February 11, 1939. Meanwhile, back in Berlin, Hahn and Strussmann published their chemical findings in January 1939. They reported the presence of barium but offered no clear explanation for how it got there. They noted that, as chemists, they hesitated to propose something as radical as a nuclear splitting because it contradicted current understanding of nuclear physics. The physics community was electrified by these discoveries. Hahn had found barium. Meitner and Frisch had explained it as nuclear fission and calculated the enormous energy release. Within weeks, physicists around the world were rushing to confirm and extend these results. And then came an even more crucial realization. If a uranium nucleus, when it split, released not just energy but also additional neutrons, and if those neutrons could then cause other uranium nuclei to split, which would release still more neutrons, then you could potentially have a chain reaction. Each fission event could trigger multiple new fission events, growing exponentially. A Hungarian physicist named Leo Szilard, working in the United States, immediately grasped the implications. He had been thinking about chain reactions since the early 1930s in a different context. Now, with nuclear fission confirmed, he realized that a sustained nuclear chain reaction might be possible, releasing enormous amounts of energy very rapidly. This could be either a source of power or a weapon of unprecedented destructiveness. Experiments quickly confirmed that several neutrons, on average 2 or 3, were indeed released in each fission of uranium-235. A chain reaction was theoretically possible. Whether it was practically achievable depended on many factors, including the purity of the uranium, the geometry of the arrangement, and the presence of materials that might absorb neutrons before they could cause additional fissions. Within months, with war looming in Europe, several physicists began to realize that this discovery had massive political and military implications. If a sustained chain reaction could be achieved, and if it could be controlled, you'd have a nearly limitless source of power. If it couldn't be controlled, or if it was deliberately designed to release its energy as fast as possible, you'd have a bomb more powerful than anything humanity had ever created. The race to understand and harness nuclear fission was on, and it would lead to the Manhattan Project, the development of nuclear weapons, and the dawn of the atomic age. But that's a story that takes us beyond the peaceful science we're focusing on tonight. For our purposes, lying here in the quiet darkness, let's appreciate the pure science of the discovery. Hahn's careful chemistry, Meitner and Frisch's theoretical insight, the elegant explanation of how a nucleus could split when given just a small nudge of energy from an absorbed neutron. The confirmation that mass could be converted into energy on a scale never before achieved. It's worth noting the role of Lise Meitner in this story. Despite her crucial theoretical contribution explaining Hahn's results, despite her decades of collaboration with Hahn, she was not included in the Nobel Prize that Hahn received in 1944 for the discovery of fission. This was partly due to the chaos of wartime, partly due to Hahn's desire to distance himself from his exiled Jewish colleague in Nazi Germany, and partly due to the gender bias of the era. History has since recognized her essential contribution, and element number 109 is named Meitnerium in her honor, but it was an injustice that she was excluded from the highest recognition at the time. As your thoughts grow slower and your body grows heavier with approaching sleep, consider this discovery as a moment when humanity's understanding of nature took a profound step forward. We learned that the supposedly immutable atom could not only be split but could release energy in the process. We discovered a new way that nature operates at the nuclear level, and we gained knowledge that would both benefit and haunt humanity for generations to come. How nuclear fission actually works. Let's slow down and explore more deeply the actual physical process of nuclear fission, how it happens at the level of protons and neutrons, why certain atoms split more readily than others, and how the energy is released. This understanding will help you appreciate both the elegance of the physics and the reasons why nuclear fission has the properties it does. Remember that an atomic nucleus is held together by the strong nuclear force, which operates only at very short ranges. Protons and neutrons in the nucleus are packed closely together, and the strong force binds each nucleon, as we call protons and neutrons collectively, to its immediate neighbors. But protons also repel each other through the electromagnetic force because they all carry positive charge. In lighter elements, these two forces roughly balance. The strong force binding nucleons together is stronger than the electromagnetic repulsion between protons. But as nuclei get heavier, containing more and more protons, the electromagnetic repulsion grows. Every proton repels every other proton, with the force diminishing with distance but extending throughout the nucleus. Meanwhile, each nucleon only attracts its immediate neighbors through the short-range strong force. This is why very heavy nuclei are unstable. The electrical repulsion is only barely overcome by the strong force. These nuclei exist on a knife edge, held together but ready to break apart if given the right trigger. Uranium-235, one of the isotopes used in nuclear fission, has 92 protons and 143 neutrons. Its nucleus is large, and the balance between forces holding it together and forces tearing it apart is delicate. When such a nucleus absorbs a neutron, it becomes uranium-236, which exists in an excited, energetic state. Think of the nucleus as oscillating, with the absorbed neutron's energy causing it to vibrate. These vibrations can cause the nucleus to distort from its usual nearly spherical shape. It might stretch out into an elongated form like an egg. As it does so, the two ends of the elongated nucleus move farther apart. Here's where the different ranges of the two forces become crucial. The strong force, being short range, now acts less effectively between nucleons in opposite ends of the nucleus. But the electromagnetic repulsion between protons doesn't diminish nearly as much with the slightly increased distance. The repulsive force wins, pushing the two ends farther apart. At a certain point, called the saddle point in the jargon of nuclear physics, the nucleus is stretched so much that it can't return to its original shape. It's committed to splitting. The nucleus breaks into two fragments, which fly apart at high speed, driven by their mutual electrical repulsion. These two fragments are called fission products, and they're typically not equal in size. A common split of uranium-235 produces one fragment with about 95 nucleons and another with about 140 nucleons, though many different mass splits are possible. Both fission products have far too many neutrons for their size. Remember, heavy nuclei need proportionally more neutrons than light nuclei to remain stable. When a heavy nucleus splits, each fragment has roughly the neutron-to-proton ratio of the original heavy nucleus, which is too neutron-rich for a lighter nucleus. These excess neutrons are ejected almost immediately. A typical fission of uranium-235 ejects 2 or 3 neutrons very quickly, within a fraction of a microsecond. These are called prompt neutrons, and they're crucial for sustaining a chain reaction. If each fission on average produces more than one neutron that goes on to cause another fission, the reaction can sustain itself and even grow. But even after ejecting these prompt neutrons, the fission products still usually have too many neutrons. Over time, ranging from fractions of a second to minutes or longer, these products undergo beta decay, where a neutron converts into a proton, emitting an electron and an antineutrino in the process. These radioactive fission products, gradually decaying towards stability, are what constitutes nuclear waste in nuclear reactors. The energy released in fission appears in several forms. The bulk of it, about 85%, is the kinetic energy of the two main fission fragments. These fragments are electrically charged and fly apart at about 3% of the speed of light, which is still enormously fast. As they plow through surrounding material, they collide with other atoms, transferring their energy as heat. About 3% of the energy goes into the kinetic energy of the prompt neutrons. Another 3% appears as gamma rays released at the moment of fission. The remaining energy shows up in the radioactive decay of the fission products, released over time as beta particles, gamma rays, and the recoil energy of the decaying nuclei. Not all uranium is equally likely to fission. Natural uranium is a mixture of isotopes. About 99.3% is uranium-238, with 92 protons and 146 neutrons. Only about 0.7% is uranium-235. The difference of 3 neutrons has profound consequences. When uranium-238 absorbs a neutron, becoming uranium-239, it doesn't usually fission. Instead, it typically undergoes beta decay, eventually becoming plutonium-239. Uranium-238 can be made to fission if hit with a very high-energy neutron, but it won't fission with the relatively low-energy neutrons produced by fission of other nuclei. Uranium-235, on the other hand, will fission when struck by a neutron of almost any energy, even a very slow neutron. This makes uranium-235 fissile, meaning capable of sustaining a chain reaction. This distinction between uranium-235 and uranium-238 is crucial for nuclear technology. To make nuclear fuel for most reactor designs, or to make nuclear weapons, you need to enrich the uranium, increasing the percentage of uranium-235. Another isotope that's fissile is plutonium-239. Though it doesn't occur naturally in significant amounts, it can be created in nuclear reactors when uranium-238 absorbs a neutron. Plutonium-239 was used in some of the nuclear weapons developed during World War II and is used in some reactor designs. The chain reaction that makes nuclear fission practically useful depends on a delicate balance. Each fission produces 2 or 3 neutrons on average. If, on average, more than one of these neutrons goes on to cause another fission, the reaction grows exponentially. This is a supercritical chain reaction, and it's what happens in a nuclear explosion. If, on average, exactly 1 neutron from each fission causes another fission, the reaction is self-sustaining at a steady rate. This is a critical chain reaction, and it's what nuclear reactors aim to maintain. The reactor produces energy at a constant rate, with the number of fissions per second staying constant. If, on average, less than 1 neutron from each fission causes another fission, the reaction dies out. This is a subcritical state. Controlling the reaction rate in a nuclear reactor involves managing how many neutrons are available to cause fissions. Neutrons can be absorbed by control rods made of materials like cadmium or boron that readily absorb neutrons without fissioning. Moving these rods in or out of the reactor core changes the number of free neutrons and thus controls the reaction rate. The geometry and arrangement of the nuclear fuel also matter enormously. If you have too little fissile material, or if it's arranged incorrectly, too many neutrons will escape before causing fissions, and the chain reaction won't sustain itself. There's a critical mass below which a chain reaction can't be sustained. The energy released by nuclear fission is truly enormous on a per atom basis. A single fission of uranium-235 releases about 200 million electron volts. While this sounds like a tiny amount, consider that there are about 25 septillion atoms in just 1 gram of uranium-235. If all of them underwent fission, it would release energy equivalent to burning several tons of coal or oil. This energy density is what makes nuclear fission so remarkable, both as a source of power and as a weapon. A small amount of material can produce vast amounts of energy. This characteristic has shaped geopolitics for the past 80 years and continues to influence decisions about energy policy, weapons proliferation, and international relations. As you drift closer to sleep, your mind perhaps wandering between waking and dreaming, think about the intricate physics happening inside atomic nuclei, the careful balance of forces, the quantum mechanical nature of nuclear states, the conversion of mass into energy, the emission of particles that can trigger further reactions. All of this, orchestrated by the fundamental laws of physics, playing out in the hearts of atoms too small to see but powerful beyond what our ancestors could have imagined. The peaceful applications. While the development of nuclear weapons understandably receives much attention in the history of nuclear physics, nuclear fission has also found many peaceful applications that have benefited humanity. As you settle more deeply into relaxation, let's explore some of these positive uses of our understanding of atomic nuclei and nuclear processes. The most prominent peaceful application is nuclear power generation. As of the early 21st century, nuclear power plants provide about 10% of the world's electricity. These plants use controlled nuclear fission to heat water, producing steam that drives turbines to generate electricity. Unlike fossil fuel power plants, nuclear plants don't emit greenhouse gases during operation, making them potentially valuable in addressing climate change. A nuclear reactor contains fuel, typically uranium enriched to about 3 to 5% uranium-235, arranged in fuel rods. These rods are immersed in water, which serves both as a coolant and as a moderator. water molecules slow down the fast neutrons produced by fission, making them more likely to cause additional fissions in uranium-235. Between the fuel rods are control rods made of neutron-absorbing materials. By adjusting how far these control rods are inserted into the reactor core, operators can precisely control the rate of the fission chain reaction. The reactor operates in a critical state, with fissions occurring at a steady rate, producing heat at a constant level. The heat from the fission reactions heats the water, which either boils to produce steam directly or transfers its heat to a separate water system that produces steam. This steam drives turbines connected to electrical generators, producing electricity. Except for the heat source, the process is similar to coal or natural gas power plants. Nuclear medicine represents another crucial peaceful application of nuclear physics. Radioactive isotopes, which have unstable nuclei that decay and emit radiation, are used both for diagnostic imaging and for treating diseases, particularly cancer. In diagnostic nuclear medicine, a patient is given a small amount of a radioactive tracer, often attached to a molecule that accumulates in specific organs or types of tissue. As the radioactive isotope decays, it emits gamma rays or positrons. Detectors outside the body can detect this radiation and create images showing where the tracer has accumulated. For example, technetium-99m is widely used in medical imaging. Its decay produces gamma rays at an energy that's easy to detect. It can be attached to various compounds to image bones, the heart, the brain, and other organs. The images reveal how these organs are functioning, helping doctors diagnose diseases. Positron emission tomography, or PET scanning, uses isotopes that decay by emitting positrons, the antimatter counterparts of electrons. When a positron encounters an electron, they annihilate each other, producing two gamma rays traveling in opposite directions. Detectors around the patient can pick up these gamma rays and reconstruct a three-dimensional image of the tracer's distribution in the body. PET scans are particularly useful for detecting cancer and studying brain function. Nuclear medicine isn't just for diagnosis. Radiation therapy uses the damaging effects of radiation on cells to treat cancer. Cancer cells, which divide rapidly, are generally more susceptible to radiation damage than normal cells. By carefully directing radiation at tumors, doctors can kill cancer cells while minimizing damage to surrounding healthy tissue. External beam radiation therapy uses machines that produce high-energy radiation directed at tumors from outside the body. But sometimes, radioactive sources are placed directly inside or very near tumors, a technique called brachytherapy. Small sealed sources of isotopes like iodine-125 or palladium-103 can be implanted in prostate cancer. For instance, delivering radiation directly to the tumor while sparing nearby organs. Another form of treatment involves radioactive isotopes that naturally concentrate in specific organs. Iodine-131, for instance, is taken up by the thyroid gland. Giving a patient radioactive iodine-131 allows radiation to destroy overactive thyroid tissue in hyperthyroidism or to treat thyroid cancer. Beyond medicine, radioactive isotopes are used in scientific research in countless ways. They serve as tracers to study chemical and biological processes. By replacing a normal atom in a molecule with a radioactive isotope, scientists can track where that molecule goes and what happens to it, all without significantly altering the molecule's chemistry. For instance, carbon-14 can replace normal carbon-12 in organic molecules. Since carbon-14 is radioactive, researchers can detect it and follow the molecule's path through chemical reactions or biological systems. This technique has been invaluable in understanding photosynthesis, metabolic pathways, and countless other processes. Radioactive dating is another important application. Carbon-14 dating, which you may have heard of, allows archaeologists to determine the age of organic artifacts up to about 50,000 years old. Living organisms constantly exchange carbon with their environment, maintaining a steady ratio of carbon-14 to carbon-12. When they die, this exchange stops, and the carbon-14 gradually decays with a half-life of about 5,700 years. By measuring how much carbon-14 remains, scientists can calculate how long ago the organism died. Other isotopes with longer half-lives can date older materials. Potassium-40, which decays to argon-40 with a half-life of over 1 billion years, is used to date rocks and determine the age of geological formations. This technique has been crucial in establishing the age of Earth and understanding geological history. Industrial applications of radioactive isotopes are surprisingly common. In quality control, radioactive sources can detect flaws in materials without damaging them. For example, gamma rays can pass through metal welds, and detectors on the other side can reveal cracks or voids that would weaken the weld. Irradiation of food using gamma rays can kill bacteria and other pathogens, extending shelf life and improving food safety. This process doesn't make the food radioactive, just as X-rays at the dentist don't make your teeth radioactive. It's simply using radiation to kill microorganisms. Smoke detectors in homes typically contain a tiny amount of americium-241, a radioactive element. The americium emits alpha particles, which ionize air molecules in a small chamber. This creates a small electrical current. When smoke enters the chamber, it disrupts this current, triggering the alarm. Scientific research uses particle accelerators, descendants of Cockcroft and Walton's pioneering device, to study the fundamental nature of matter. By accelerating particles to very high energies and smashing them together, physicists can probe the internal structure of protons and neutrons, discover new particles, and test theories about how the universe works at its most fundamental level. These accelerators have led to discoveries like the Higgs boson, a particle that helps explain why other particles have mass. They've confirmed predictions of quantum field theory and have pushed the boundaries of human knowledge about the nature of reality. As you lie there in the comfortable darkness, your breathing slow and steady, you might reflect on how the same scientific knowledge can be applied in so vastly different ways. The understanding of nuclear fission that led to weapons also led to medical treatments that save lives, to power plants that provide electricity, to research techniques that advance human knowledge. The story of nuclear physics is a reminder that scientific knowledge itself is neutral. It's a description of how nature works. How we choose to apply that knowledge, whether to heal or harm, to create or destroy, to benefit or exploit, depends on human choices, human values, human wisdom or lack thereof. And as the weight of sleep presses more heavily upon you, as your thoughts become more diffuse and dreamlike, perhaps you can appreciate the wonder of the nuclear realm without the burden of its darker applications. Can marvel at the intricate forces operating inside atomic nuclei, at the transformation of mass into energy, at the quantum dance of protons and neutrons. can feel a connection to the scientists who unraveled these mysteries, driven by curiosity and the desire to understand nature more deeply. As we bring our journey through the atomic world to a gentle close, let's take a moment to appreciate what we've explored together. From the vast emptiness within atoms to the dense nuclei at their centers. From the birth of elements in the hearts of stars to the discovery of how to split atomic nuclei here on Earth. From the quantum uncertainty of electron clouds to the precise experiments that revealed the atom's structure. You've heard the story of how ancient Greek philosophers speculated about atoms without the tools to test their ideas. How chemists in the 19th century gradually built up evidence for atoms' existence. How physicists in the early 20th century probed inside atoms and discovered electrons, then nuclei, then protons and neutrons. You've followed the path that led to understanding nuclear fission, from Rutherford's gold foil experiment revealing the nucleus to Chadwick's discovery of the neutron, to Cockcroft and Walton's first artificial splitting of atomic nuclei, and finally to Hahn, Strussmann, Meitner, and Frisch's discovery that uranium nuclei could split in two, releasing enormous energy. You've learned that you are made of stardust, that the atoms in your body were forged in stellar furnaces billions of years ago, that you are a temporary arrangement of ancient matter, a brief pattern in the endless cosmic dance. You've glimpsed the strange quantum realm where particles exist in probability clouds, where exact prediction is impossible, where reality itself seems to shimmer with uncertainty. And perhaps most importantly, you've spent this time allowing your body and mind to relax, to let go of the tensions and worries of the day, to drift on the gentle current of this story towards sleep. Your breathing has slowed. Your muscles have released their tension. Your thoughts have grown hazy and unfocused, exactly as they should as sleep approaches. The atoms in your body, those ancient travelers through space and time, will continue their journey. Tomorrow you'll wake, and those atoms will power your thoughts, your movements, your interactions with the world. But for now, they participate in the quiet processes of rest and restoration. Your body knows how to sleep. It knows how to heal and refresh itself. You don't need to do anything. You can simply allow it to happen. As you sink deeper into sleep, you might imagine those atoms, too small to see but too numerous to count, all working together to keep you alive, to keep you stable, to keep you you. Each one vibrating in its quantum state, bound to its neighbors by forces fundamental to nature, part of molecules, cells, tissues, organs, systems, all integrated into the magnificent complexity that is a living, breathing, dreaming human being. Let your last conscious thoughts drift away like leaves on a gentle stream. There's no need to hold on to anything. No need to remember what you've heard. It will be there if you want to return to it. For now, just let go. Let the darkness deepen. Let sleep wash over you like a soft blanket. The universe continues its expansion. Stars continue to fuse lighter elements into heavier ones. Neutron stars collide in seed space with gold and platinum. And somewhere on a small planet orbiting an ordinary star, you rest peacefully, your atoms borrowed from the cosmos, dreaming whatever dreams may come. Before you go completely, just a gentle reminder. If you enjoyed this journey through the world of atoms and the story of how scientists learned to split them, please consider liking this video and subscribing to the channel. Your support helps us continue creating these deep, relaxing explorations of science and the wonders of our universe. But don't worry about that now. There will be time for that later. For now, sleep. Deep, peaceful, restorative sleep. Your breathing continues, slow and regular. Your heart beats steadily, pumping blood through your body, carrying oxygen and nutrients, powered by the chemistry of atoms. And all of this happens automatically without any effort from you. You can simply surrender to sleep, knowing your body will take care of itself. The atoms that make you who you are will be here when you wake. They're going nowhere. They're yours for now, these ancient bits of stardust, these quantum dancers, these split-able yet stable building blocks of all matter. And with them, you'll greet tomorrow, refreshed and restored by tonight's sleep. Good night, rest well, dream sweetly, and may your sleep be as peaceful as the gentle quantum dance of electrons in their probability clouds, as ancient and patient as the atoms themselves.